First interaction we're going to be looking at today is the Compton scatter interaction. This is one of the two interactions that is within the diagnostic range of X-ray. This is when an incident photon interacts with an outer shell electron, which therefore ejects it, and now this is called the recoil electron. The leftover energy is going to be exiting as a scattered photon, which is the leftover of the incident photon in a different direction and a little bit less energy. So during this interaction, it does not depend on the atomic number or size of the atom. It will take place on all different sizes of atoms. It also, when kVp is increased, this interaction is increased. And when this recoil electron is ejected, it causes scatter, aka backscatter radiation also, which is responsible for our occupational dose. These scattered X-rays also affect the image. They produce a uniform optical density and intensity that results in reduced image contrast, aka radiation fog. The second interaction we're going to be looking at is the photoelectric absorption interaction. This is when an incident X-ray interacts with an inner shell electron, and the incident X-ray is totally absorbed and it ejects this inner shell electron, which is called a photoelectron. And this photoelectron escapes with kinetic energy that is equal to the difference of the incident X-ray and the binding energy of the electron. This interaction cannot take place unless the energy of that incident X-ray has greater or equal energy to the electron binding energy. So this is more likely to happen when energies are close to each other. When X-ray energy is increased, the amount of photoelectric effect is decreased, aka so when you increase your kVp, there will be less photoelectric effects going on. And also, for this interaction is more likely to happen in higher atomic numbers. So after this photoelectron is ejected, there's a vacancy on this inner shell here now, so therefore these outer shell electrons have to fill in these spaces, and when this is happening, this transformation of energy is being kicked out as this characteristic radiation right here, which is also very low energy secondary radiation, which is no benefit to us. Alright, so the third interaction we'll be looking at here is the coherent scattering interaction. This is a very low energy interaction, and it is the first out of the last three that is not diagnostic. So Compton and photoelectric were in diagnostic range, and this one is not. This is also called classic scattering. This is when the incident photon interacts with the electrons and causes the atom to vibrate and get excited. This then triggers the release of a secondary photon with the same energy, wavelength, frequency, but in a different direction. So since there is not an electron leaving this atom, it is not ionized. And this scatter radiation usually does not reach the IR, so it's little significance to diagnostic imaging. The next one here we'll be looking at is pair production. This is when the X-ray photon is converted to matter in a form of two electrons. So a very high energy photon with at least 1.02 MeV is required for this interaction to take place. This is a very high interaction. This is when the incident photon interacts and comes close with the nuclear field and loses its energy, which creates a pair of these electrons that you see here. So we can just pull these out and say this is our positron, which is a positive, and this is our negatron, which is negative. The positron then pairs with a negative electron and gives rise to two photons moving in the opposite direction, while the negatron is just going to join up with an atom that needs a space filled. And this positron reaction that I was talking about is called the annihilation reaction. And finally, we have our last reaction, or interaction I should say, and it is photodisintegration. This is also when the incident photon here is interacting with the nuclear field. And this is also an extremely high energy photon, above 10 MeV. The high energy photon strikes the nucleus and all the energy is absorbed in here. The excited nucleus responds by releasing a nuclear fragment, throws it right out of there. Because of the high energy level needed, it is not relevant to diagnostic imaging. And that is the 5 reactions that I'm going over today.